All right. Well, thank you everyone for joining us today. Welcome to the Intelligent Edge webinar with STMicroelectronics, Edge Impulse, and Avnet. Jongboom and Raphael Apfeldorfer are here today with us to share a little bit about TinyML integration in the STM32 ecosystem and walk you through some demos of it in action. Jan is an open source developer and technology evangelist working on TinyML as CTO of Edge Impulse. So over the past years, he's gone up and down the stack from embedded to web to everything in between. He's a strong believer of open source, has written thousands of patches for open source projects, including Mozilla Firefox OS, JavaScript, and ARM Embed. Raphael is the head of AI solution marketing at STMicroelectronics. He is working on solutions bridging the gap between embedded developers and machine learning to bring intelligence onto low-powered IoT devices. In his previous roles, he worked for 20 years in telecom and IoT industries with a focus on mobile broadband and LPWAN connectivity, security, and low-power applications. So just a little bit about this event today. The first half of this event will be a presentation complete with TinyML demonstrations, and the last half is going to be open for questions. So if you do have questions during the event, there is a little section, a little icon on the bottom of your screen that says Q&A, and you can just click on that and type your question in there. So that's where we're going to see most of your questions. If you do type them in the chat, we might miss them. So we kind of just ask you to use that Q&A section there so we make sure that we get all of your questions answered. And today we also have Zach Shelby in the background. He's the CEO of Edge Impulse, and he'll be joining us just to kind of answer some questions. So he'll be typing to you if there's some questions that are easy to answer over text. All right. So just an additional part of this webinar, STMicroelectronics is giving away 20 ST IoT discovery boards. So anyone who attends this event live with us is going to be in the running to get one of those boards. And winners will receive an email later next week with more information on how to claim that prize. So the great thing about this board is that it is supported by Edge Impulse. So whatever you learn in today's webinar, you can use to get started developing right away if you are one of those lucky winners. So thanks again for joining us, and I'm going to let Jan take over from here.
Wonderful. Thanks so much, Katie. Yeah, I would love to welcome all of you here in the webinar. It is fantastic to see how many of you registered and how many of you are showing up here. And I hope that today, Raphael and I will be able to give you a wonderful kind of some insight in where TinyML fits in the industrial play, and actually show some demonstrations of machine learning really running on the lowest and smallest devices possible. So yeah, my name is Jongboom. You can reach me here at jan@edgeimpulse.com. Prior to founding Edge Impulse, I was at ARM. And while we were there, we saw one thing happening. One, lots and lots and lots of microcontrollers ship every year. I think ARM alone is doing 22 billion chips every year, not going into large computers, the ones that's sitting on your desktop or even the one that's sitting in your pocket with your mobile phone, but rather really tiny embedded microcontrollers that are embedded in everyday products, like my piano that I have sitting here. Like even the pedal of my piano that you use, the sustain pedal, has 3 chips in it already. Pretty amazing. We also saw that while the number of devices that we ship goes up every year significantly, the capabilities, the hardware capabilities of these devices are pretty astonishing. Like a typical industrial sensor is, thanks to new MEMS sensors that come on board, ST ships beautiful MEMS sensors that are really, really tiny, come in a very small footprint and are very accurate. We've gone to devices like a typical industrial sensor that you can buy here in 2020 as a vibration sensor on less than a square centimeter that can measure vibrations up to 1,000 times a second. It has very accurate temperature sensor, which is really hard to do. Like if you ever build a small circuit yourself, one of the very first one is that you'll probably use an analog thermistor to sense the temperature. But these ones are accurate to maybe 2 degrees Celsius, which is not very useful if you actually want to use it in an industrial setting. But now we can actually get small and really accurate digital temperature sensors for very cheap price, actually. This device even, it's pretty cool. It's made by a Japanese company, is water and explosion proof. Wonderful. I'm not entirely sure how they tested it as really explosion proof, but wonderful to read that in the datasheet. And it can even, thanks to LPWAN, what Raphael worked on, the LoRaWAN and Sigfox and Airmet IoT, we can now send data 10 kilometers from point A to point B, as long as there's line of sight, using 25 milliwatts of power. And that paired with processors that get faster every year. So the processor in a typical product like this these days is capable of running over 20 million instructions per second, if you're looking at a Cortex M4. But while the hardware on these devices is getting more and more capable, what we actually do with these devices, it seems to be getting less and less every year. Because this device out of the box sends the average motion once an hour, it sends the peak motion once an hour, and the current temperature once an hour. Which is kind of a waste of this beautiful hardware. But the whole reason of that is that lots of these embedded systems have constraints. They either have cost constraints. You can't actually send all the data to a central location because it's too much data. You have bandwidth constraints because maybe you're running on LoRaWAN, or you're running on Sigfox, so you have a few messages a day that you can actually send. Or power constraints. You're running off a battery, and thus what you can do with the device is completely dominated by how often you drive the radio. So we are able to capture all of this data, lots and lots of sensor data, sometimes up to 1,000 times a second, and then we actually discard almost all of it and just send a very simple conclusion over. And that also means that lots of really interesting events get lost. So this is a small graph of accelerometer data. If the only thing that I care about is the peak motion, then that data point, that little spot there, is the only thing that I'm going to send over. And that's probably not the most interesting event. This, for example, would be much more interesting to me because it looks different than all the other data that I collected in this time window. And also, if you try to compress this down to say, well, let's do average motion, these can be very misleading numbers. Here are two different things that I was actually doing with the ST IoT Discovery Kit dev board. One is just moving it up and down. The other one is making a circle. The average motion in both of these signals are actually completely the same. So 3.36 meters per second and 3.35, the root mean square of the signal. So if you actually want to up the usefulness of these devices, and we know the constraints of these devices in these environments, the only way to actually up the usefulness is to put some of this intelligence, the things that we want to measure, onto the device. So rather than this device having to send raw sensor data over, which is not possible because of the bandwidth and the power constraints, or sending the average or the peak motion over, which is not useful because we throw away so much information that is potentially can potentially help us, for example, identify a fault state on a machine. Much rather, we want this device to be capable of answering questions like, based on the data that I've just collected, I've seen a vibration pattern that's going to lead to a fault state a week from now. It might be that the temperature varies in a way that I've never seen before, which is much more interesting than just, here is the temperature that I've just collected now. Or this machine oscillates different than all the other machines in the factory, and do a comparison there. And that also means that after that, I only need to drive the radio when I see that something is going on. The fact that my device is sending a message is actually an indication that there might be something wrong. And now we can compress all this data, the hours worth of, in this case, vibration data, into a single byte, which means that we need to send less often. So we don't need to drive the radio every hour if we only need to send a message when something is wrong. So that saves a lot of power, and we can use that excess power consumption budget to do some of this on-device intelligence. And it saves a lot of our actual network bandwidth and maybe even costs when driving this down, because we can reduce the amount of data that we actually need to send. Instead of 12 bytes, 4 bytes for the current temperature, 4 bytes for the peak motion, and 4 bytes for the average motion, I only need to send a single byte. So what can we use to kind of achieve that? Well, over the last couple of years, we've realized that machine learning is really great at finding patterns in messy data. And messy data, for me, is kind of anything you can't reason about in Excel. If you have some temperature data that is slowly rising, and at some point it hits the threshold. Okay, and you can easily reason about that in Excel. Great, don't use machine learning for that. But anything else, like really messy data, it's very useful. However, machine learning is also associated with this. You know, dozens and dozens of GPU instances sitting somewhere in a data center crunching numbers. Luckily, two really brilliant folks got to a similar idea. 2 years back, more or less, Pete Warden, who was working at Google at the time, and Neil Tan, who was working at ARM at the time, came to the same idea, and they figured, well, what if we can actually bring machine learning to these smaller devices? So for Pete, his inspiration was, okay, Google. I'm very sorry if now everyone's phone actually activates. But for Pete came into Google through an acquisition, and he was looking at like cool stuff that was happening internally in Google. And he got to talk to the team that was developing the OK Google keyword spotting model. And this is actually not running on the main processor on your Android phone. It's actually running on a separate DSP chip. So it's always on without actually having to drive the main CPU while you're not doing anything with it. And when he realized that you could actually run this on the DSP, he figured, okay, well, how can we turn this into something where we can run multiple other models, except for this keyword spotting model, on here? And Neil was doing a similar thing within ARM. They realized that if you just focus on the inferencing, so just on, I have a machine learning model and I want to run this on device and just tell me what your prediction is, that is not that is a process that you can do pretty efficiently. In essence, a machine learning model, if you look at it, is just a mathematical function with lots of parameters. It's like if you have a function to see if the temperature is above or below 25 degrees, that is pretty simple. You have one parameter, which is kind of your threshold value. You can see the same thing with machine learning. It's just a mathematical function with lots and lots of parameters. And while you're training, you're constantly tweaking these little parameters in the function. But once you've found the optimal value of these parameters, other than that, it's just a mathematical operation, just a bunch of vector multiplications. And as we said on like the first slide, these even small IoT devices, small embedded systems, can now do 20 million operations a second. So asking it to just execute this mathematical function can be really, really fast. So that was our initial premise. Then we realized that you can actually trade accuracy for speed. So while you're tweaking this mathematical function, we want to use 4-byte floating point numbers. But actually after, when we want to run the inferencing on device, we can just reduce that to 1-byte information because it's not that important anymore. Thus lowering memory requirements are going a lot faster. We realized that there's lots of parameters in a network that don't really contribute much. Some of these parameters don't contribute much to the actual outcome, so we can remove those. And then we figured, okay, well, now all we have are 8-bit vector multiplications, and that's something we can do really fast in hardware. So we worked on adding hardware optimized paths to this code. That is what ST has done as well. We'll demonstrate a little bit later. And all of this kind of targeting battery powered microcontrollers. So super cool movement where the TinyML community is still relatively young. But some really, really, really brilliant minds working on making this a reality. And all of a sudden we can now do things like predictive maintenance on device. So anything that rotates, maybe you have some ultrasounds, you can capture data, compare that to what is normal behavior or what is abnormal behavior, and then identify when something is amiss. We can do stuff with audio on these devices. So that even on small microcontrollers, these are fast enough to even do real-time audio classification. Like one of our community members is doing something with a microphone sitting in a pipe in a factory, and they can actually hear when something is amiss, maybe too much air is blowing through it. So really wonderful. So, and then the video stuff. So Raphael will tell a bit about their lone worker monitoring systems.
Yeah. So yes, actually, we can also implement some vision algorithms even on these microcontrollers. So another use case, for instance, is the lone worker monitoring. Typically in industrial environments, it's very useful to detect if people are present in restricted areas or outside expected hours. And you don't want to trigger false alarms due to movement unrelated to human activity. So that really is a way to filter this out. And we added that example in our FPI Vision 1 pack available on the ST website. The use case actually runs on Cortex-M4 and M7, depending what level of performance and image classification you want to have. So yes, next we wanted to focus a bit about the industrial use cases where the TinyML fits. It's actually very beneficial to make local decision at the endpoint itself to react in real time to anomalies without a strong dependence on connectivity as well. So we do micro analysis, micro decisions on the MCU itself, or even sometimes inside the sensor itself, that is able to do really tiny detections for simple ways. And then in an industrial use case, typically you would have also industrial gateways where you take these meso-level decisions, taking into account all of the data coming from the different devices together, and you have a bit more processing powers. And then you would choose whether to convey data directly or even the events that are based on your decision to the outer cloud for even more macro level decisions. So next in ST, we have a portfolio that covers all of these different industrial use cases for both the endpoint and industrial gateway. So we have basically a range of sensors for basic variable acquisition as well as smart sensors. And on the MCU side, we cover different things like AI, connectivity, security, or general processing requirement for your data. So typically in this range, you would find microprocessors for more the industrial gateways, like the STM32MP1, which is a dual Cortex A7. We have also a wide range of MCUs that are suitable for industry, from the high performance MCUs where you need best-in-class system performance and some hardware acceleration for the DSI, motion JPEG, this type of things, or even LCD screens. You have the wireless MCUs that incorporates also connectivity inside the MCU SoC with BLE or LoRaWAN support. And then we have the mainstream MCUs that are used for real-time control applications such as motor control, power conversion designs, and ultra-low powers as well when you have dynamic voltage scalings to balance between power consumption and processing demand. And the MEMS, also you have a full set of environmental, vibration, and acoustic sensors that are very highly accurate, like I mentioned, water resistant, or also very consistent into the bandwidth they have. So having a wide bandwidth, but also a flat one is very important in order to be able to do the measurements that are necessary for precise anomaly detection in this type of environment. So yes, most of them are suitable for this vibration analysis, for instance, monitoring motor imbalance, bearings, gearboxes, lubrication, or venting occlusions, this type of things. And all of these components are benefit from the 10-year longevity commitment by ST. So that's really something we bring for industrial use cases, and where typically you would run this type of intelligence. Next, we have also ready-to-go boards with industrial sensors. So I wanted to introduce the ST-Win, which is our wireless industrial node. That's a board that embeds already all of the industrial grade sensors you can think for getting started fast with a proof of concept. On this, you have ultra wide bandwidth 3D vibration sensors, 3D accelerometers, gyroscope, magnetometers, humidity and temperature sensors, and also some connectivity via the BLE on board or Wi-Fi expansion board. So you have everything you need to get started with this type of boards and get to prototype quickly with the Edge Impulse SDK.
Wow, thank you, Raphael. So yeah, hopefully you're not super enthusiastic. You're like, wow, wonderful. I understand the use cases, I understand what I can. What do I need to actually start building this model? Well, first of all, I'd like to say that like everything starts with raw data. If you're currently sampling data every 10 seconds from your IoT device and sending it over, not good enough. Like as Raphael said on the ST-Win, for example, there's a SD card slot to do data logging. Some other ways that we do it, for example, in the IoT Discovery Kit, there's a Wi-Fi radio. So we can stream data from a sensor directly to a central location, doesn't really matter, but get data at the highest resolution possible. Even if you're looking at something like vibration data, you see that your accelerometer can do maybe 200 hertz or something, get data at that resolution. It's a lot easier to downsample later than to upsample data. There's lots of other little interesting things that you're otherwise throwing away. So start with raw data, get data at the highest resolution possible. Then second, you might think, okay, well, I'm an embedded engineer. I've been doing embedded software for the last 20 years. Like, why do I all of a sudden need machine learning for doing some on-device intelligence? And I completely agree. We have been doing on-device intelligence and drawing conclusions on devices for a very, very long time. And it would be foolish to kind of throw away that accumulated knowledge within the community. So my next step will always be, after you got the raw data and you already know what features could be meaningful. If I have vibration data, probably running an FFT over my data and then looking at the peaks in the FFT or at the spectral power density, yes, wonderful, great idea, do that first. So if you have a way of extracting some meaningful features, do that first. Use proven DSP algorithms. So an example of a signal processing pipeline could be that while I have a keyword here, about a second worth of audio data captured at 16,000 hertz, and I convert that using mel frequency subsalt coefficients into a spectrogram of features. Not only, like, the biggest benefit here is actually that it reduces the number of features significantly. So we go from 16,000 or 32,000 kind of bytes, 16,000 times 16-bit numbers, to just 240 features. And it also helps kind of get rid of the noise. So raw data can be super messy, right? So this is me doing a couple of things with my dev board, doing a fist bump, moving it up and down and drinking a beer. If I look here, plotting my raw data in a graph, I can kind of see that, okay, well, beer, there's a little bit more movement on the z-axis, and I see like fist bump a little bit clumped together there, but it's very hard if I have one of these little dots to tell me like which of these three categories it belonged to. If literally the only thing that I do with this data is I do a fast Fourier transform over the data and then plot the height of the first peak on the X, Y, and Z axes. Very, very simple, like DSP 101. I can already separate this data much, much better, which you can see here on the right. And that means that a machine learning algorithm at a later point can also much more easy separate this kind of data. So always think about feature extraction as your second step. And then third, let the computers figure it out. So I see this in a way is a computer is much better at finding thresholds than we can, and can make much more fine-grained thresholds than we can. If I'm writing an algorithm that needs to run on an embedded system, and then maybe 4 or 5 variables, that is something I can keep in my mind. But a computer might be able to find like 2,000 parameters and do a much better fit. But there are many different kind of problems that you might have that have different solutions here. So it's not just machine learning as one magic algorithm. For me, it's kind of, you can separate this in 3 things. One, what is happening right now? A classification problem. Is this behavior out of the ordinary, which is an anomaly detection problem? Or what will happen in the future, which is a forecasting problem? Like, all of these can be done by machine learning, but there's different algorithms that are good at different things. So for classification, you probably want to use a neural network. So if I have like a full pipeline would look, I have raw data coming in at 16 kilohertz. I then extract the interesting features using MFCC, and then I feed into a neural network that will then learn to classify, have I heard yes, or have I heard no, or have I heard something else? But neural networks are not the only game in town. So, and very often, like classic ML, older ML algorithms are much easier to explain. So if you want to do anomaly detection, actually clustering all your data together, you'll see a nice cluster here. And when new data comes in, compare that to known clusters. It's something that's much easier to explain, and it's kind of like a thresholding algorithm, but with much more fine-grained thresholds. You see like 32 clusters actually come together. For forecasting, look at something like regression. So don't think that neural networks are the only thing in town. So once you've done that, you captured your data, you've extracted features, and you learned from this data using a machine learning algorithm, like finally deploy that to device. So what we can do with Edge Impulse and STM32Cube AI is actually take all the signal processing code, take any neural networks that you might have, any other ML blocks like anomaly detection, and then package that up together in a single C++ library. And that's the moment that you can actually run that on device. So very last step, take all of this, take your learnings, and only then put it on device. So Rafael will tell a bit about how about STM32Cube AI and how Edge Impulse fits in there.
Yes, thanks, Jan. So let me add a bit more information about the deployment on the STM32Cube environment. So typically for proof of concept, as you've seen, Edge Impulse also is a great way to get started because you get a full cloud solution, a low level of coding you can deploy straight out of the box on your ST-IoT node. But then maybe for productization, when you run toward the industrialization steps, you want to find back an ST environment that you are more used to for developing embedded software. So that's where we have integrated Edge Impulse framework with ST solution. So Jan will show you the different deployment options, but one of them is the export via the STM32Cube AI. So for neural networks, ST is providing a tool called STM32Cube AI that converts the model generated and trained with the Edge Impulse into an optimized C model. And this conversion is transparent to you because the tool is directly called in the cloud and exports optimized C code as a CMC spec library. Then this library can be imported into STM32CubeMX and be used in the full STM32Cube environment. So you benefit from all of the configuration, the porting to different STM32 MCUs, some low-level code generation or configuration by the UI. You can add your application code on top with the IDE of your choice and have a wide range of available tools for programming, debug, or monitoring the code execution. So basically, you fall into the STM32 ecosystem that is really funded on both having simple hardware, a set of hardware development boards for fast prototyping, and a lot of code examples that come with it. And then also the STM32Cube with a set of PC software development tools that run on any OS with tools like CubeMX, IDE, Programmer, Monitor, and the corresponding embedded software that run on the device and let you have not only abstraction layers and portable code, but also some middleware stacks as well coming from either from ST or the open source market for the RTOS, USB, TCP, IP, and so on. And all of these hardware abstraction layers was tested in an industrial level grade with Code Sonar from Grammatech. So this is really industry standard and have safer implementation with the examples. Then the STM32Cube AI is an expansion tool that comes as an expansion of CubeMX. So it converts neural networks into optimized C code for both memory and performance on any of the STM32 MCUs. So you import from the framework supported by Edge Impulse or any framework really that is supporting ONNX open format. And then the tool is called in command line and direct conversion with default parameters, or you call the tool from the UI and when you have imported in CubeMX Cube AI environment. For instance, you can get the exact inference time, the CPU load for a selected MCU, and if you provide your training or evaluation data, you can also validate the neural network code generated. You can directly validate it on target and check its accuracy. So you have a lot of nice tools in the UI also when you need to really tweak. You can dimension your network if you want to review the model layers or check what is the RAM or flash memory usage. You can optimize your code because we provide very light runtime libraries in terms of footprint and also bring some specific optimization for STM32 or generic optimization like quantized models to reduce RAM, flash, and latency. And then finally, some fine tuning where you can control finely where you allocate your memory, review the split between internal, external memory, have some fine control on the weight mapping, and also update your model without a full firmware update. So basically, that will give you an access to all of the MPU and MCU portfolio, and you can map then your use cases according to this portfolio. Typically, a lot of ML and AI techniques can be deployed. You typically deploy a simple use case based on vibration on the extremely small Cortex-M0 at 48 megahertz. There is very little RAM. The audio anomaly detection you will run rather on the Cortex-M4 or L4 Plus, on which we even have a person detection demo, so the start of the imaging processing. And then for the image processing and even video, you can run on Cortex-M7 at 400 megahertz. It's you're running even in less than 256 kilobytes of RAM. So this is really fitting MCUs you would find in typical industrial environments. And for the microprocessor, that's where we target more industrial gateways typically.
All right, thank you, Raphael. So, all right, time to get started. So if you actually want to start building along, that is even possible. So we need some hardware, naturally. So the STIT Discovery Kit is a really nice board to get started because it has a Cortex-M4. So as Raphael said, actually fast enough to do biosignal analysis, vibration analysis, audio analysis in real time, and even like some person detection and like small vision models. So this one has a 80 megahertz processor, 128K of RAM, so plenty for everything that we're going to do today. And has a bunch of sensors, so it has a MEMS microphone, MEMS accelerometer, and other IMU sensors, so really cool. If you don't have that board yet, or you're still waiting for your order to be shipped, you can also use any modern smartphone. So that's cool. Everything that we're going to be building today, you can build with your phone as the sensor. And if you have a different device, maybe you have a different ST device, you can actually run this with our SDKs on any other device. So look for the data forward to get data off device. And when we deploy this model, we'll just get a CubeAI CMSys pack, and it will run on any STM32 as long as it's an M4, M7, M33. So straightforward. This is an easy way to get started. So Edge Impulse, what we'll be using in the demo, we see it as kind of TinyML as a service. You're an embedded engineer. You're not a data scientist. You already have devices in the field. You care about device flow. We are embedded engineers that turned to the dark side and went to do machine learning, and we built tooling to help you kind of do the same thing. So we allow you to capture data from real sensors in real time. So you have open source SDKs for that, like data logger functionality, but you can also get data that you already collected from your device in the field. We allow you to build a valuable data set. Your data might be worth a lot, not maybe just for the company, but even wider. Like actually building up this data set can actually add like IPR value for your company. We then help you to design a signal processing and a machine learning pipeline to actually extract the right features and make predictions and stuff from that. We call it an impulse. Help you to test that on real devices in real time, actual data flows. And then finally help you deploy that with the help of STM32 CubeAI and actually deploying that on your edge devices again. So we have end-to-end tutorials. I'm going to show some cool things here in the platform, but we have end-to-end tutorials on vibration, audio, and vision to go from zero to model basically in an hour for each of these things. So, all right, let's exit the presentation here. Let's open my browser. What I have here is the IT Discovery Kit. So this device is connected over USB cable to my computer. It runs a data logger application. So we've written firmware for this board to do data logging from its sensors. And we have a small daemon running on my computer that then sends that data straight to Edge Impulse. So when I go to the Devices tab, I see that Jan's desk is currently connected. And the little green dot means that I can actually control this device straight from the UI, which means that I can start sampling data without having to do anything on device. I just send a signal, the device gets it, samples data, and goes through. So let's actually build a model. So as I said earlier, like everything starts with data. So yeah, here we're going to be building a small gesture model, something I could do behind my desk. I'd love to bring in a large industrial machine, but as you can see, we're currently in my living room due to the whole COVID crisis. But the same principles actually apply when it comes to doing predictive maintenance on anything that rotates. We're going to be using a very similar feature pipeline. So yeah, if my device is connected, I can select my device, I can add a label, a sample length, so how long do I want to start capturing data, the sensor that I want to capture data from, here the accelerometer, and the frequency. So let's actually start with some idle data. An idle set is always required. Like if you build a keyword spotting model, for example, and you want to know yes, no, or neither, you will need to have some baseline data, some noise, for example. Same happens actually if you build predictive maintenance models. Make sure that you actually capture what is normal as well. Similar with vision models, if you want to know like person or no person, make sure you capture like kind of lots of random information. So idle, we got there. Let's actually do some wave data. So now let's wave my sensor. And we do this until we kind of have a data set of about 15 minutes worth of data. I've done the data capture earlier already, as you can see. And with what we have now in our data set is just raw accelerometer data labeled with the gesture that we're doing. So this is wave data. This is some wave data too. Here we have some up-down data. The other movement that we put in here was snake. So snake is just me moving my device over my desk. And then naturally idle. So idle doesn't need to be completely idle. It might be me typing. But in the end, we've captured about 15 minutes worth of data over 4 different labels. And with 15 minutes of data is actually good enough to build a model that performs surprisingly well even on device. So, but there's one problem here with the data. Naturally, this is pretty noisy. Accelerometers are noisy instruments. So let's actually start building a kind of an impulse, something that can classify this data. The very first thing is saying that we're dealing with time series data. And what I want to do with this data, so I captured data of various lengths. So I had some 10-second samples, some 5-second samples, some 20-second samples. For this, I kind of capture my gesture in about 2 seconds. That's kind of a window that is long enough for me. So what I can do is I take a 2-second window. I slice all my data up in 2-second windows. I use a sliding window to go over this data to kind of artificially up the number of data samples that I have. And that's the very first step. So slice up your data. Then I want to add a processing block. So here, I said I want to do stuff, kind of, I want to look at like the motion that I have. And I want to look at kind of a spectral analysis pipeline. This is very similar to what you'd be doing on vibration data on, for example, a motor. So fast Fourier transform over the data, look at power spectral density, etc. There are different processing blocks for different types of data, including audio data, image data, but it's also possible to add a custom block. And these can be written in any language. So if you already have a signal processing pipeline that you're currently using, it's very easy to plug this into Edge Impulse. So add it here, and then we want to learn from this data. So add a learning block here. Let's do a neural network because we want to classify what we're doing. So I save this. Then on the spectral features page, the first thing that I want to do is denoise my data. So I set a low pass filter, standard. As you can see, if I do a high pass filter, only the noise is there and my actual movements are gone. So a low pass filter at 3 Hz cutoff frequency. Then I want to run an FFT over my data. Look at the frequency domain. Here, I store the peaks here, the height and the location of these peaks. And then the spectral power density in buckets between 0.1, 0.5, 0.51, and 1, 2 Hz, and 2 and 5 Hz. So these would be very similar to the features you'd normally do with an FFT from the accelerometer. So save that and let's generate these features. So what we do now is we take the data, all the data in the data set, slice it up in these 2-second windows, and then run a feature extraction step over this. So we run the FFTs and the power spectral density code out of it. And then we generate 33 features, so actually very little data, 33 features per sample. So once that is done, we can actually plot the data here. And we can plot some of these features together. So here we're looking at accelerometer data, so I can look at the root mean square on the X, Y, and Z axes, and I really see clusters forming. So what we said earlier, like after your feature extraction pipeline, you kind of want to see data already separating. I'll show this a little bit later also for very high dimensional data like audio. That's kind of cool. And if you want to like, okay, I see like a cluster here that's a bit different than all the other data, so I can click on it. It shows me the sample that it was collected from in the actual waveform for the 2-second window, or I can click here and see, okay, well, indeed, this is a bit more noisy. It's still wave, but maybe done on a different device or by a different person. So not necessarily a bad thing. So with that, I can then learn from this data. So let's train it for a single cycle so I can show some of the output while we're training it a little bit more. A neural network, as said earlier, has kind of lots of parameters that we can tweak. And the number of these parameters are the neurons in the network. So we can edit those here. Or if you know what you're doing, or you have a data scientist with you, you can just click the switch to Keras expert mode. And that will give you a just a code editor where you have the full Keras neural network API available, or just edit the IPython notebook. And at that point, you can just edit it as a notebook. Your data scientists probably know what. So while we're training, let's look at this little graph. So naturally, if we train for only a single epoch, so for one training cycle, our neural network doesn't know anything. Like all the little parameters are still in a random state. So our confusion matrix is that sitting here at the bottom, basically says, well, we either guess idle or snake. So this doesn't perform very well. The interesting part here is though that we can show the on-device performance. So once we've trained the model, we kind of have one big mathematical function with lots of small parameters, but throwing data into that function and then getting a result out is just some vector multiplications. So here I have, if we run a quantized model, so we change all the internal weights to 1 byte, we can kind of run this inferencing in about a millisecond and requiring about 4K peak memory usage and a binary size of 3.5K. If we look at some of the other models while we're training, like audio data, we can do in about 14 milliseconds. So that's just the inferencing time of the network. You still need some time to do the signal processing pipeline. But even on Cortex-M4F, this is fast enough to do real-time audio classification like 20 times a second. So you can do this on streaming audio with a memory size of like 13K. And pretty great. And even for complex models like vision models, this is measured on a Cortex-M7 instead of an M4, but we can do this with like under half a meg of memory, and this is even on a large model. Like if we're using a smaller model or we're using a grayscale model, we can get this down to about 120K, which is great because that even gets in reach of Cortex-M4. We're almost done training here, so we see that our loss in accuracy is going up, so we're almost done training. We save our best performing model. And now our accuracy actually shoots up to 99.5%. So really good. How good actually? So let's test it out. So let's do some live classification. And we're going to be doing some snake movements. So here I capture data. All right. Sorry if that was very noisy to you. So we classified all of this actually as snake 16 times. So really cool. Great. If you want to like drill down to it and like see, okay, what does it compare to in the rest of my data sets, then you can dive into here, but at least the classifier seems to work. Now, there's one thing where neural networks are really bad at, and that's data that I've never seen before. So if I now actually start shaking my device vividly, the network actually classifies all of this as wave, and that naturally that is not correct. But the neural network doesn't have any knowledge of this is data that is unlike anything I've ever seen, so I don't want to classify it. It just classifies either one of those 4 classes. So neural networks here are not enough, and I think that's very often the case if you're going to deploy millions of devices, especially in environments where you can't really touch them anymore, like an industrial setting. to always have like a safety guard sitting here. So if I'm looking at my model, fortunately, or at my features, I can see that this cluster is very far outside of any known data. And that's something that we can use to our advantage. So I can say, add a second block, a learning block, one where I want to do anomaly detection. And this is a classic ML algorithm. Save it. Train this on the 3 axes that I just saw, just for clarity. Hit start training. And now we cluster all the data, and now we can compare data coming in to these known clusters. So my snake data earlier is sitting nicely, the orange data is sitting nicely in my cluster, definitely not an anomaly. My shake data, though, is outside of any of these known clusters, so this is definitely an anomaly. And this way we can actually override what we're doing in the neural network and have like a safety guard before deploying. So we've tested our model. We know that the classifier works. We've tested this in real time from the ST device. Actually, let's deploy this to device. So as Rafael said, we've integrated Edge Impulse with STM32Cube AI. So what this lets us do is package all of our code up. So that's the signal processing code. We automatically, for the blocks that we ship, for vibration data, audio data, and image data, we'll use Siemens DSP to make this run as fast as possible on ST MCUs and other ARM core MCUs. And then we use STM32Cube AI to run the neural networks. And then we have some custom code to run our classic ML algorithms. So this all integrates as a single CMSS pack. You can add that in STM32Cube AI with the rest of your project. I'll show that in a sec. First, I'm gonna just build a binary for the ST-IoT discovery kit so you can see all of this in action. So what we do here, if you have this IoT discovery kit, we can build a firmware project, including all the optimizations, and kind of give you a single binary that you can run on device. So let me save that. And then I drag this file onto the DisL for IoT board. Right now it's flashing. And once we have that, we'll actually have this full model running on the device, completely local, no connection to Edge Impulse or anywhere required. And calling it is kind of as easy as calling a single function. I'll show it in a little bit in Cube AI. It's just sensor data in, and you get probabilities out. So let me stop my little daemon, so I have access to the serial ports. So this is a view of the boards. There we go, super cool. And I can run Impulse to now run this inferencing locally. So what we see here while it's sitting, so it's sitting idly on my desk. It gives me a probability of 0.93. For that, it gives me an anomaly score of -0.4, which is great. But see how incredibly fast this is. So this is doing 2 seconds of vibration data in less than 20 milliseconds, running on a Cortex M4F. So really cool. Let's actually test if it really works. So right now, it's still sitting idly. Now I'm gonna pick it up. Let's do some up and down. Cool, 100% up, down. Let's do some wave. And now let's shake it a little bit to test our anomaly detection code. Something went wrong there, but at least we see here up-down movement 100% of the time, waving and idling. So really good in classifying exactly what is going on straight here. So that's the kit. If you include this in STM32Cube AI, what you're going to get is a CMSS pack. I hope this is visible because my screen is a little bit big. But you get a CMSS pack that you can add like any other pack, like the ARM packs for CMSS DSP or anything, included in your project. After you add it, it will show up as a middleware pack here. So it comes with the Cube AI model, so the full neural network. It comes with the Cube AI runtime. So there's the headers, and we see the actual libraries for the Cortex M33, M4, and M7. Your other model parameters like anomaly blocks, DSP configuration, etc., and our Edge Impulse SDK, which kind of binds everything together. And after that is literally just a single function call. So you construct the signal where you tell us like how long it is and where we can get the data from, like a buffer in memory or flash if you do stuff on device with limited memory. And literally the only thing we need to do is call the run classifier function. After that, we give you these predictions, and you can just You give the probabilities, you can just run them straight. So super easy and incredibly fast. So we can do real-time vibration on an M0 Plus even. We can do real-time audio classification on a Cortex M4. And we can run real-time image classification on color images, even object classification, for example, on an M7. So really, really, really cool stuff. So if this super inspired you, go start building something, and there's even more to that. So you can join the ST-Win challenge and actually start building a real machine learning product with the ST-Win. Sorry, Rafael, and actually compete to win prizes worth over $500,000, which is super, really, really cool. You can sign up at the Innovation World Cup here at the link below, and we'll send the slides out. So a little recap here of the last 15 minutes. First of all, the machine learning hype is real. Machine learning is not only incredibly useful, it's gotten to a state where we can actually run this in real time on devices and actually classify things that happen around us better than we could previously. It is also the perfect fit together with sensors. Sensor data is messy. The real world is messy. Machine learning plus sensors is a perfect fit. So literally go and start using the remaining 99% of your sensor data and do that by going to edgeimpulse.com. Start building a model or go to ST, buy some hardware, and I think together this is absolutely fantastic. I've said mind-blowing many times over the last couple of weeks while we're building new models that really run here. And with that, thank you all, and let's hear it for Q&A.
Oh, great, thank you, Jan. I started talking and I realized I was still muted, so I got it sorted out though. We're good. So we have a lot of questions. We've had amazing interaction here on the Q&A section. Let me see if I can find some good questions for you. So one question is Edge Impulse free or pay on the go?
That's a good question. So Edge Impulse is free for developers. We have an enterprise version of it for teams that really value their data and want to collect this data and want to do team collaboration. But for developers, it is free, and it will remain free.
Great. Is it possible to use the Edge Impulse site with other STM32 boards, such as STM32F746 Disco? Anything like that?
Yeah. So it's really easy. So we have it's really easy to capture data from these devices. We have a little thing called the data forwarder. Just dump data over serial from the boards, and we'll capture it. And running this will run on any M4, M7, or M33 using Cube AI. So you just get it as a normal CMSIS pack, as you always do in STM32 Cube AI.
Great. Is there any power profiling option on the Edge Impulse platform?
I'll leave it to Rafael. Not Edge Impulse, but
yeah. Okay. Well, after you have indeed exported as a CMSIS pack and imported in the Cube STM32 Cube environment, yes, there is all the tools you need to really optimize your embedded code. There's a tool called STM32 Cube Monitor Power that will let you optimize your power consumption.
Great. All right. How does Edge Impulse support data labeling?
So we try to do labeling like as early as possible. So when you're already capturing the data, label it straight away. So we do that. If you have one of the dev boards that we support, like the IT Discovery Kit, we'll make this really easy in the studio. Otherwise, we have some endpoints to just dump new data in. And it's recommended to do the labeling straight there. Or we have a UI to do this if you have like audio data or something where you want to do it. But my suggestion would always be do this as early as possible, because then everything is still fresh.
Great. What's the difference between BL4 SSI IOTA 01A and BBL4 SSI IoT 01? So I guess A versus.
It's the LP WAN or the sub-gigahertz radio. One of them is 915 megahertz for US. One of them is 868 for Europe. So great. Make sure you buy the right one for your region.
How much data do you need to build a model from images?
Actually, very little. So we use a thing called transfer learning to, we trained very generic models that kind of already understand shapes and colors and contrast, stuff that every visual model kind of needs. And then we strip off the upper layers of the network, and then we only retrain those with your images. And it generalizes very well. So we've seen actually for like two object detection, so two actual objects. I have my lamp and my plant there as one of the examples, and some noise data. With about 100 images, we can actually get something that that works really well. So pretty great for kind of all kinds of computer vision applications.
Great. What is meso actuation? Meso?
You're muted, Rafael.
Oh, you're muted.
Yeah, so it's just a way to present what are the different levels in which you are doing either the data processing, or where you take actuation, so that's decision, and actually use actuators to apply these decisions. So the meso was just the middle one, with the one you would apply at the industrial gateway level.
All right. Can we use device driver development on STM32?
I'm not sure I get the question, but yes, I mean, on the STM32, once you've integrated the STM32 Cube toolset, you will have everything you need in terms of low-level drivers, hardware abstraction layers, and yeah, and even middleware, actually.
All right. Can you please also briefly talk about the recently released image classification vision capabilities in Edge Impulse? Does that require heavy computing resources?
It depends a little bit. So as said, we kind of use transfer learning to make this train faster, and also give you kind of a size choice early on. So you can, based on like kind of the compute capabilities of your device, you select like a base neural network, and then we run that. What we see is Cortex M. I would recommend a Cortex M7 for doing this stuff because it will just run fine. It is possible to get, if you have a very specific use case, to build a model that is small enough to fit on a Cortex M4. But typically M7 and above can do this stuff in real time, 10 frames a second even sometimes. So.
Great. How do we reduce power consumption during inference? If the device goes to sleep, how do you trigger it to not miss the event?
Rafael, you want it? No. Kind of. How do you? Yeah, I think it's still a combination of knowing like when to wake up and see something. So I know that like some of the ST accelerometers. I'm not sure if the one on the IT Discovery Kit has it. They can wake up if they see a certain amount of motion, trigger an interrupt, and then capture data and then classify that. Or do duty cycling here as well. So don't sample all the time, but sample for 2 seconds every minute or so, if what you do is not time critical. But yeah, you still need to be a bit smart about it because you can't drive the MCU constantly.
But you're right, and there are some smart sensors that are able to wake up only when they see things happening. So that's what I wanted to say about the different levels of intelligence you can put some in the sensor that is very low power to preserve the power of the overall system as well. And that's valid at all the different stages of the system, of course. And of course, bear in mind that the processing is often consume even less power than the transmission on some of the wireless radio as well. So sometimes just be doing the analysis locally rather than transmitting all of the data over wireless is already a gain in power consumption.
All right. Is there a step-by-step tutorial for Jan's gesture capture demo?
Yeah, absolutely. So if you go to docs.edgeimpulse.com and you click the Getting Started link, there are end-to-end tutorials on both the gesture detection, on real-time audio classification. So we do scene detection, like is my faucet on or off, like something you can do in your house, and even image classification. So little end-to-end tutorial on actually classifying 2 different objects in your house and how to build that. So super easy to get started. And the IT Discovery Kit supports both the vibration and the audio use case. So it's a great little book.
I just threw that link in the chat as well. For those of you who are interested. I think we have time for maybe one more question. This is a great one. Where can we learn more about TinyML? I assume this is the docs. You also have a forum, right?
So yeah, we do actually have so we have docs, we have forums. I'm very active there. So if you ask a question about TinyML, I'm super happy to answer. There's also the kind of TinyML Foundation, and they organize bi-weekly or every 2 weeks, they organize talks, TinyML talks. And those are super informative. So these are people either from the industry or people from academia, just talking about like new developments in TinyML, new model types, new sensor types, etc. So definitely check that out. Just TinyML talks.
Great. So there are still a lot of questions open that we didn't get to. And so if we didn't get to your questions, I did just post the link to the forum on edgeimpulse.com over on the right-hand side. And make sure you go check that out. And then we will also be sending an email following this probably later in the week with a link to the recording and also any sort of access to the Q&A. So I think Jan said he would maybe write up some answers to some of these most common questions, and we'll have those out to you so you can kind of get some more feedback on that there as well. So thank you, Jan and Raphael, for joining us today. This was really great. We enjoyed it a lot.
Katie, thanks so much. And thank you all for watching.
Bye.
Guys.